Hi everyone, this is the final presentation for Team 5. The product we choose to analysis is the plug machine. The plug machine is designed to enhance soil preparation process in gardening and small-scale farming. Equipped with a motor change drive system, the plug machine propels itself forward. When backend and lowered, the clutter remover engage with the earth to loosen the soil and remove weeds. Our target customer will be home gardeners who manage personal gardens and individual farmers who manage small-scale farmers. They all have the need to prepare the soil. For the first diagram, we create a diagram that shows the main function of the plug machine that should perform. The plug machine should be able to break and turn soils, which is most important part. We can see from the function component mapping matrix that many parts shares the same function as support weights, transmit powers, and reduce vibration. This shows what parts we should consider to improve.
As mentioned earlier, the two customer groups have different needs and demands. One of member of our product family will be for breaking and turning dry and rough soil full of unwanted weeds, and the other members of the family will be for breaking and turning the looser and healthier soil. To do this, we will make the cutter and remover a modular component. Using the function component mapping matrix, we identify the module part will be drive the parts different between the varieties. As the picture on this slide, we can see that the different modules provide different function to suit the different customer needs. So the framer and the remover was redesigned to become a uniform parts, allowing us to delay product differentiation, so we can assemble the frame and the remover later.
We analyze assembly procedures to find the highest impact parts on the manual assembly time. The top contributor are engine, handles, and cutter remover. The base is selected as the platform and should be considered to be redesigned due to parts consolidation. As we can see in the quote chart, these parts are ideal for redesign. In the function component mapping matrix, the base and frame share the same function to support weight of the plug machine, so we try to combine one of them with other parts together. Starting with the platform, the base. The original design took 60.76 seconds to assemble, considering wheel shaft and structure shaft assembly with fasteners. We improved the design by reducing part counts, preferring snap fits, and reducing part variety. This redesign has no impact on the function of the part, and the manufacturing cost will reduce because we changed its main shape from a quadrilateral to a triangle. After the DFA process for the base, we cut down assembly time to 33.63 seconds. Moving on to the second part, the remover. It needs 2 screws to screw with the frame, and it takes 32.5 seconds to assemble. So we consider to combine the frame and remover into a whole part. We improved the design by reducing part counts and fasteners, preferring snap fits, as well as reducing part variety. The assembly time reduced to 33 seconds compared to the former 45.5 seconds. The remover now will have the function to support weight of the plug machine for the absence of frame.
Here, I will be discussing the design improvements we made for automatic assembly of two key components, and the engine and the handle. For the part selections, we choose to analysis the engine and handle since they are all considered in high function importance. In our DfM analysis, we found that the assemble cost for engines and handles are $50.64 and $20.13, which shows that there is room for improvements. For the engine part, we modified the exhaust pipe so that it is easier to insert into the engines. And we also modified the screw holes to make them easier to access. We also cut the corners in the base so that it can be rotated better. With these modifications, the installation cost was reduced from the original $15.64 to $13.16. At the same time, the functions of engine parts was not changed, but the manufacturing cost of the engine part will increase due to these operations. For the handle parts, we cut out the slots to reduce the use of screws when installing the handles. This can reduce the installation cost from $20.13 to $8.66, but these operations will also increase the manufacturing cost.
methods that are viable for a folded aluminum shape are sheet metal work, electromachining, and conventional machining. Electromachining does not meet the tolerance specifications, and that leaves us with sheet metal work and conventional machining as the two options for manufacturing. We picked sheet metal work as it is usually cheaper and the stock size of the metal would be too large for large-scale machining. The tolerance of the base was selected with respect to the distance between the engine mounting holes. This is because the engine is the part we do not manufacture in-house and is the most vital component that cannot be altered, so therefore it needs to be mounted correctly to have its weight supported by the base. Proper mounting also ensures vibration reduction. The chosen tolerance is 0.5 mm as the diameter of the hole is 15 mm. For the handle, we selected injection molding as it is the best candidate for the circular hollow plastic shape with a large batch size. For the handle component, the most critical dimension is the height of the female connection cavity. We did not pick the width as this degree of freedom was already constrained by a screw hole. The cavity needs to properly fit from the male part of the base structure without any wiggle room to optimize handling, properly facilitate steering, and improve ergonomics.
No redesign was made as the brake handle design fits the injection molding criteria. DfM Pro identified 3 design recommendations focusing on the draft angle and wall thickness. The cost of the injection molding per part before the redesign was 15 cents per part. Following the design guidelines, the handle is redesigned with a uniform wall thickness that is under the nominal wall thickness of 3 mm. Sacrificing functionality, the screw hole and the previous inner contour were eliminated. This leads to a drastic reduction in cost per part by almost 150%. The base was redesigned before the DfM analysis to ensure its developability for metal sheet work. After this initial change, the cost of metal sheet working per part comes down to $6.93 per part. DfM Pro gave 8 instances of cut-out distance to part edge warning. For redesign, the overall sheet thickness was reduced from 10 mm to 7.5 mm. In addition to that, the bulge around the bottom shaft hole and fillets around sharp edges were added. These adjustments combined solve the cutout distance to part edge warning. After the redesign, there is a 12% decrease in cost per part. Unfortunately, hubs were unable to provide instant quoting on both parts. This is likely due to a redesign error and should be solved later in the report.
Of this product service system integrates a maintenance kit subscription, delivering essentials like eco-friendly oil and cutters in recyclable packaging, reducing waste and costs. Additionally, field service teams provide on-site repairs, extending the machine's lifespan and cutting replacement costs, making the system more economically and environmentally responsible.